Welcome to Jillian Helms's ePortfolio number 2, Chapter 4 Summary. Here we are discussing boundary work. We know that boundary work is equal to the integral of P dV using volume, or mass times the integral of P dV using specific volume. If there's a constant pressure process, you can pull the pressure out of the integral, and you end up with the boundary work equals to the pressure times the change in volume. If there's a linear increase in pressure, which can be shown as a piston cylinder device with a spring, the boundary work is equal to pressure 1 plus pressure 2 divided by 2 multiplied by the change in volume. Here we are given two more equations for constant temperature ideal gas boundary work. Boundary work is also known for being the area under the curve on a PV diagram. In Chapter 4, we are working with closed systems. This allows us to write an energy balance where there's Q in minus Q out plus work in minus work out equals delta U. And since the system is stationary, there is no potential nor kinetic energies. For work, we use the convention that expansion is work out and compression is work in. Change in enthalpy for a constant pressure process can be written as such. Delta H equals delta U plus boundary work. This can be for expansion or compression. This can be written as Q minus boundary work equals delta U, which using the equation above allows us to see that Q equals to delta H. Specific heats are given as Cp and Cv. Cp is the specific heat at a constant pressure, and Cv is the specific heat at a constant volume. We know that specific heat has different relationships depending on which substance you're using them for. We can use them for ideal gases, solids, or liquids. For an ideal gas, we know that the change in internal energy is equal to the Cv in terms of T times dt. And the change in enthalpy is equal to Cp in terms of T times dt. R is equal to Cp minus Cv, and K, which is the ratio of the specific heat values, is Cp over Cv. For incompressible substance, such as solids and liquids, there are multiple different ways of writing this for both change in internal energy and change in enthalpy. For all four processes, isothermal, which is constant temperature, isometric, which is constant volume, isobaric, which is constant pressure, and adiabatic, which is no heat transfer, we have the Q value, heat transfer, work value, and the change in internal energy. Here are all of these equations shown relating Q, W, and delta U in terms of specific heats. We know that delta U is 0 in an isothermal process because Q minus W equals delta U. Since Q and W are the same, the change in internal energy is 0. For an isometric process, we know that work is 0 since the volume is not changing. In an adiabatic process, we know that there is no heat transfer, therefore Q is 0.